Hey guys, welcome back. I don't know about you, but when I first saw the first harmonic drive mounts come out and you had a telescope on one side and no counterweights on the other side, this picture is the one that kept coming to mind. And I thought, man, there's no way I'm doing that. Well, since then, I've bought a ZWO version of a harmonic drive, the AM5N. And so I thought I'd take some time today to go over the real story behind the AM5N weight limits. I've been through the documentation they have. I've come up with some differences in my interpretation. And for the first time ever in doing a video, I'm going to put this disclaimer out there that these are the opinions of this guy and not of ZWO. First thing we're going to start off in today's video is looking at some of the design considerations that you might want to think about if you're designing a harmonic drive with a payload on one side and no counterweights on the other. What are some of the things you ought to be thinking about? Then we'll take a look at what ZWO says they thought about, and we'll take a look at those limits and how they all stack up. And then we'll take a look at the motor torque required for guiding and for correcting periodic error and compare that with the kind of torque you need to lift a heavy SCT off from the meridian and no counterweights on the other side. And then we'll look at overturning caused by wind. And then finally, I'm going to provide a bit more detailed recommendations for the AM5 and how you use the payload and counterweight combinations. Use these at your own risk. Definitely check in with ZWO support before you do anything that deviates from what they would seem to suggest. I came across a lot of surprising findings about the AM5 and, most surprisingly yet, about PhD2. So let's get started. There are three top level design considerations that I have in my mind when I look at a harmonic drive mount. One of them is structural. I'm sure that the ZWO engineers performed what's called a finite element analysis of the AM5N and looked at different payloads on this side and different counterweights on this side. A finite element analysis tells you what the stresses are throughout the mount body and, probably much more importantly, what are the deflections. There are tiny displacements going on in and around this body that you can't see, that can't be seen because they're too small, but yet may be significant enough to impair the operation of the gears. And that's one of the things that I suspect could possibly drive what is the upper limit of the payload that you could have, or what is the upper limit on the counterweights you can have and where they can be placed. A second consideration is motor torque. We all know that the harmonic drive mounts generate a lot more torque than, say, our German equatorial mount. But the question is, do you have enough torque capacity to lift an OTA with no counterweights on the other side and still be able to overcome friction and execute the guiding commands sent to the mount? With a typical German equatorial mount, this number here is 0. And friction and guiding are all that the German equatorial mounts have to deal with. Harmonic drive mount's a different beast and has to handle this big unbalanced torque on one side. And then finally, we'll take a look at stability. All of these design considerations, and I'm sure many others the folks at ZWO considered, lead to restrictions on the maximum payload you can have, the counterweights, where to place them, and the offset distances. There's a quick look guide that comes with the mount. Of course, there's the manual you can download off of their website. Let's take a look at this little area over here, precautions. It says if you have a payload that weighs more than 15 kilograms, then you need to use a counterweight, and that the total payload capacity should not exceed 20 kilograms with the counterweight. Now, one of the interesting things right off the bat that I like seeing here is that there is a call out for the maximum output torque of 30 Newton meters. That's a very important number, and it's going to play a big role in our discussion on this topic here today. Now, over in the manual, it says 15 kilograms, of course, without the counterweight, 20 with, but it goes on to provide a little more detail in that the counterweight is placed at 25 centimeters from the RA axis. And from the website, we have two very useful pictures that frankly should be in the manual. But what it's saying, and this is a key assumption that ZWO is making, whether you have a payload at 15 kilograms, it is located 20 centimeters from the RA axis. Or if you have a 20 kilogram payload, it also is located 20 centimeters from the RA axis. The second thing this graphic does is actually showing you that there is a counterweight and it's placed 25 centimeters from the RA axis. Here they say the counterweight can be less than or equal to 5 kilograms. The second thing that they show here is that the counterweight bar, and I'm sure they mean really the distance between the counterweight and the RA axis, should be no more than 25 centimeters. One other piece of information I saw in the documentation is that the center of gravity of the load, including the counterweights, so payload plus counterweights, the center center of gravity should be within a 25 centimeter lever arm. Lots of numbers here. Let's just summarize them and then we can go forward from there. Obviously, the max payload less than 15 kilograms. If you're not going to use counterweights, you can go up to 20 kilograms with counterweights. Total counterweights should be 5 kilograms, not less than. It should be 5 kilograms. And in effect, they're saying don't go higher than 5 kilograms. The total distance from the counterweight CG to the RA axis is stated to be 25 centimeters, and the maximum unbalanced torque is 30 newton meters. And then finally, that last note we read, which was that the maximum CG offset it should be within 25 centimeters of the mount. These are the two graphics that they show that ZWO shows 15 kilograms at 20 centimeters and a 20 kilogram payload at 20 centimeters. In this case, they're using the 5 kilogram counterweight at 25 centimeters. And the thing you'll note here, this 15 times the 20 times gravity is 30 newton meters. So this is the maximum unbalanced torque that they want you to abide by. And then over here with a 5 kilogram counterweight, it brings the total unbalanced torque to 27 newton meters. But what that also means is you can't really go lower than 5 kilograms because then you'll violate that 30 newton meter limit, and you can't go shorter than 25 centimeters. Otherwise, you'll violate that 30 newton meter torque limit. I've got my setups here, 7.8 kilograms, no counterweights, and my setup with the counterweights. In this case, I used two counterweights, my two EQ6R counterweights located 16.4 centimeters from the RA axis. I did that in order to balance this payload so that in the end, I have an unbalanced torque of 0 newton meters and an offset CG offset of 0 centimeters. So I am certainly satisfying the 30 newton meter requirement and this 25 centimeter requirement. But I'm violating this total weight of the counterweights. I've doubled that. Why did I ignore ZWO's counterweight recommendations? Here's that graphic that we were just looking at. We've got a 5 kilogram at 25 centimeter counterweight. This arrangement here is entirely equivalent from a structural perspective as having two 10 kilogram counterweights placed at 12.5 centimeters. So the effect of the stress, the deformation and whatnot on this mount body that we were talking about from the finite element analysis, it would be identical whether it's this configuration with twice the counterweights or this configuration. Likewise, if I put 2.5 kilograms at 50 centimeters, that too would produce an entirely equivalent structural effect. These limits just don't seem to have much tie back to physics. I think it's just a simple way for ZWO to define a counterweight configuration all users to use in the two scenarios that they envision. Go ahead and use more counterweights if you want to. Let's talk about the torque required while doing guiding. The RA motor is constantly rotating our telescope at the sidereal rate of 15 arc seconds per second. And then we get some commands coming in from PhD2. This is the guiding commands that I pulled out of a log that I was using that came out of one of my imaging sessions with the AM5. If you go into that log, you'll see a column of RA guide distance and a column for RA duration. The RA guide distance is the command that PhD2 was sending them out to move such and such arc seconds in the forward direction or in the negative direction, depending on what it needs to do to put the guide star back in the center. And then it tells it, okay, here's how much time you have to do it. So each one of these plotting symbols here is a guide pulse. It is how far to move in angular measure, in angular distance, and how long do you have to do it. And I imagine a guide pulse would look like this on this timeline here. The command would come in. There would be this delta t. This is how long you have to execute this command. And delta theta here is the amount I want you to move forward in the RA direction. It would increase the angular rate from sidereal up to some maximum number. And then that times the delta t divided by 2, which is just the area under this curve, is the offset angle that the guiding algorithm is asking for in this guide pulse. I look at this and imagine, well, this must be the guide rate. If I'm guiding at a rate of 50% of sidereal, then I'm expecting this number here to be 7.5 arc seconds per second. But yet, when I take these commands and I calculate this using this formula here to pull out what the delta theta dot is, in fact, I'm getting 8.8 arc seconds per pixel. So I don't know what's going on here. Another thing that popped up, possibly more serious, is the minimum move command. As you know that we type in a minimum move, meaning in pixels, If you get a command to move fewer pixels, and usually it's a number like 0.2, 0.3 pixels, then don't issue a command to the mount. You're probably just chasing the scene. Well, the odd thing here is that if I take that min move, which is 0.13 in this particular run, multiply that times my image pixel scale, I get 0.38 in terms of arc seconds, and that means I'm expecting no commands. None of this stuff I'm seeing here, in my view, could be going to the mount, but it is. At least the part down to here is going to the mount. And this, oddly enough, right here is 0.13. In other words, it seems that PhD2 is taking the min move number, which is supposed to be in pixels, and interpreting it as if it's in arc seconds. And then there's this weird thing where, okay, you're doing that, then why do I have this stuff here? So I don't know if these commands down here at these lower pulse width times, lower correction distances, I don't know if this is being generated separately by the predictive periodic error correction algorithm that I'm using or not. Let's get back on the track of what is the torque. We have a picture like this that tells us that we're going to ramp up the velocity, the angular velocity, up to some maximum, and then ramp it back down so we're back at the sidereal rate and tracking again. There is an angular acceleration associated with this, and it's just the slope of this line. It's this angular velocity divided by delta t over 2. That's the angular acceleration, and the angular acceleration, theta double dot, is tied to the torque, corresponding torque, by the moment of inertia, the mass moment of inertia. We were looking at those numbers at the bottom line of that table in a previous slide. This is the number we want in order to compare to that 30 Newton meter static torque that you've got to overcome when your payload is off at the meridian. Now, another thing that's nice about this linear slope that I have here, that means it's a constant angular acceleration, which means this is just a number, and this is just a number, so therefore torque is just a number. So in effect, executing a command like this from the motor's perspective is essentially PhD2 is saying, okay, give me this much torque for 1/2 of delta t, and then give me the opposite of that torque for 1/2 of delta t. So this will speed us up, and then this will bring us back down to a sidereal rate. Now, if I go back to these numbers here, and by the way, the maximum torque that's being generated is not out here at the end with these high corrections. It's actually down here with these very short time pulses here. That's what's driving the torque. This end, not this end. But if I take one of these numbers here, the maximum acceleration that I'm getting out of that is this equation here, and that turns out to be 2.25 milliradians per second. Now, a milliradian is kind of like an arc second. So that tells us what the angular acceleration is for a typical guide command, one that will generate a lot of torque. Let's look at periodic error. Periodic error is in the ballpark of a maximum of 10 arc seconds, then it goes down to a minimum of minus 10 arc seconds, back up to a maximum of 10 arc seconds, and all that happens over a period of about 288 seconds. Well, you can take this and convert that into an angular acceleration for just correcting for periodic error, and when you do that, you get this formula here, and convert that into milliradians per second squared, and a crazy thing, 2.3 times 10 to the minus 5. In other words, the angular acceleration that comes out of a guiding command is 1,000,000 times higher than what you would need to simply correct for periodic error alone. Another thing that's crazy is that when you multiply this number by what amounts to the largest moment of inertia you can put on this mount, multiply it by this, and what you'll find is that it's still a very small torque here. The torque you need in order to execute a guiding command, even the worst case guiding commands down here, is only 1% of the unbalanced torque of 30 Newton meters. The torque required to do guiding is tiny, tiny compared to the torque required to lift your telescope when it's at the meridian and you don't have counterweights on the other side. So let's take a look at the stability of the telescope with no counterweights and how much wind can we stand before this thing tips over. I've got a set of dash lines run here connecting the feet of the tripod. That's these dash lines over here. These dash lines are important, or at least the boundary is important, because if the center of mass of everything with your telescope, the payload, the counterweights, the mount, the tripod, the center of mass of that whole system falls within the boundary here, the yellow triangle, then you are stable. And this distance here is 28 centimeters. So this is kind of the origin of the statement that we saw in ZWO's documentation that if the center of gravity of the load, including the counterweight, should be within a 25 centimeter lever arm. 25 centimeters meaning going this way. Because once the telescope starts to move and go over to the meridian, and let's just say the center of gravity of the OTA is at 25 centimeters, and you have a 15 kilogram weight here. This is where the weight will be, and it's approaching this boundary. Once the weight of the telescope, the OTA, gets to this boundary here, the only thing keeping you stable is the weight of the tripod and the weight of the mount, and that's it. And a little bit of gust of wind will really ruin your day. Now, what about the wind? Well, let's consider that we have the wind coming in, blowing this way. We're at meridian. The overturning risk we're talking about is this back leg lifting off and the telescope and tripod rotating about this red line here. How much wind can we take before this thing falls over? Another thing to keep in mind, if you've got an SCT like shown here in the picture, check this number here from the RA axis up to what you think the center of mass is of your telescope, because that is getting awfully close to this 28 centimeter number. Now let's go take a look at the wind force necessary to push this thing over. This is a page from the building code used to design buildings, of course. There is a section in here for calculating wind on freestanding signs, and that's kind of analogous to what our telescope is. It's a long body with a smaller height, so the dimension is longer going parallel to the ground than vertically. The idea is that it's this body that's sitting up above the ground. Wind can go under, wind can go over, and wind can go around. And we're just looking for the force generated on this area here, the projected area of your payload. And if you go into this table here, you're pulling out, based on the ratio here, the aspect ratio, you're pulling out the force coefficient. There's also a gust response factor. Basically, the rest of this is 1/2 rho v squared. And that gives you the force acting on the telescope at center of the area of your telescope. So I did a couple of examples here. One of them we're going to take a look at is a 15 kilogram OTA, 25 centimeters from the RA axis. Okay, so that's our scenario. These curves would vary depending on what kind of configuration you're looking at. So keep in mind that this is the only configuration I'm looking at here. We don't have counterweights. We've got a 15 kilogram OTA at 25 centimeters from the RA axis. Now, down here we have two curves. This one is the OTA leaning over at the meridian, no cover on it, no telegizmos type cover on it. This curve is for the telescope at the home position, but with the telegizmos cover. And when you put the cover on, it's like attaching a sail. So this area here goes up significantly when you put a cover on it. But let's just look at this line here. As long as the overturning moment here is a positive number, you are stable. As the wind picks up in speed from 0 to 5 kilometers per hour to 20 kilometers per hour, you start losing your resistance to the wind. And finally, when the wind gets up to about 46 kilometers per hour, again, in this scenario here, or 29 miles per hour, that's when overturning is predicted to occur. It's actually a pretty high wind load. I was surprised to see that. When you park the scope and it's at the home position and you go out and put the cover on, you got a significant resistance to overturning because now the mass of your OTA is sitting right above the center of your tripod. So this distance right here with no wind kind of shows you the effect of your payload, your 15 kilogram OTA, going from home position to the meridian position. Now let's follow this line over as the wind speed picks up, and you can see it starts taking a dive much faster than the other curve, and it essentially is ready to fall over at 35 kilometers per hour or 22 miles per hour. Okay, so let's go back to the baseline recommendations from ZWO about when to use counterweights, how much counterweights, where to put it. If the payload weight is less than 15 kilograms, you don't need counterweights. If the payload exceeds 15 kilograms but is less than 20 kilograms, then ZWO is recommending that you put a 5 kilogram counterweight at 25 centimeters from the RA axis. But the thing you need to keep in mind is that these very simple statements about how to use the mount are based on assuming that the payload CG is 20 centimeters from the RA axis. So let's go take a deeper look at this. We have going across the bottom here the payload weight from 0 up to a maximum of 20 kilograms. We have a line here at 15 kilograms where we'll jump from no counterweights to needing a counterweight. And then up here is the distance that our payload is from the RA axis. As long as you're below the 20 centimeters, then very simple guidance that we looked at on the previous chart is totally applicable. Things start to get a little wonky, however, if the CG of your payload gets higher. This is what can happen. You are now violating that stability requirement that said that the CG of the payload is 25 centimeters away from the RA axis, and you're more at risk of your scope tipping over. If you are getting close to this 25 centimeter line here, go ahead and use the 5 kilograms at 25 centimeters that ZWO is recommending. Something else is happening over here on this line here, this little notch that's taken out. That's because of the 30 Newton meter torque requirement. Once you cross this line over here, especially if you're pushing the limit on the 15 kilograms, you could very easily have the CG location above this line here, and then you would be violating the 30 Newton meter torque limit. And so again, that's where you'd want to use the counterweight system that ZWO is talking about, 5 kilograms at 25 centimeters. Once we cross the 15 kilogram line, then we're supposed to use 5 kilograms at 25 centimeters regardless. But it's not that simple, because here, as we go up in CG of our payload is moving above the 20 centimeter line and it gets to this orange line, that's when you're going to violate this 30 Newton meter torque limit once again. And here I'm suggesting you put on an extra weight. And so now you have 10 kilograms of weight, which does exceed the 5 kilogram limit. But if you don't do it, you're going to be violating the 30 Newton meter torque limit. If your payload is much higher above the RA axis and you cross this green line, that's where you probably want to add a third counterweight, 15 kilograms. That's something that you want to check out with your particular setup or setups and see where you are on this plot, the weight of the payload and the center of gravity height above the RA axis. And then you can get a better idea of what your counterweight situation ought to be. Something has to give here. You're going to need heavier counterweights in order to satisfy the 30 Newton meter limit and the stability limit under certain situations. ZWO provides a couple of example setups, one 15 kilograms and not requiring counterweights, and one at 20 kilograms that does require counterweights. But they're assuming the center of gravity of those two setups is within 20 centimeters of the RA axis. I don't think the 5 kilograms and 25 centimeter numbers they provide for a counterweight configuration is a true physics-based limit. It's just a very convenient simplification that makes it easy on ZWO to define a specific counterweight configuration that most users will find will work with their systems. The 30 Newton meter torque limit and the 25 centimeter total weight offset limit seem to be the more important of the criteria that ZWO defines. So in this case, it's probably better to go ahead and increase the counterweights in order to stay within these two limits. I also took a look at the torque required during guiding, and that was an eye-opening exercise there. I didn't expect come away with more questions about PH2 than I had about the AM5 when I started this, but I think that's where I landed. I can't quite see where the guide rate manifests itself in the data that comes out of the guide log. The one area where I think seems to be a bit of a problem is that the min move parameter we set in units of pixels appears to be interpreted as arc seconds inside PhD2. Another thing that I was very surprised about is the wide range of torques that are required to work the telescope. There is, with an AM5 or harmonic drive mount in general, there is a much higher demand on torque when you don't have counterweights because you've got to be able to support the dead weight of the OTA when it approaches the meridian. The second thing is that the torque generated during guiding commands appears to be only 1% of that. So if you can provide the torque needed to handle unbalanced weight of the OTA, extra torque you need for guiding is trivial. And then periodic error turns out to be 1/1,000,000th of that. But it never fails. You want to answer one question and you end up with 4 more. Okay, guys. Well, that's a lot of information. I hope they got something out of here that you wanted. There's guys.